moment, this is a true you.
Oh, I appreciate it. That's why I love working with
Always holding you back.
you. Right, Chris, you are presenting today, right?
Yep.
So let's make you co-host. And let's wait for the team to dribble
Uh,
in. Here we go.
link.
Okay, that's looking good. What are we talking about today, Chris?
So key value representation in the brain.
Okay. I'm not entirely sure what to expect, but here
Key
we
As in
go.
like
value
in a
representation
Python
of memory
dictionary?
in the brain.
Let's see. It's going to be a surprise. So, welcome to Neuroccino 9:30-ish on a Monday morning. This is where we present exciting science that we came across to the best of our knowledge, and then we discuss it with the means that we have. So today, Chris is volunteering. Chris, if you could share thank you, the link in the chat. Take it away.
Okay. Let's do this one. Here we go.
You can zoom in a little bit more so it's full screen. Cool.
All right.
Thank you.
So for once, I'm not going to talk about LLMs and ChatGPT. It's still going to be machine learning though. So it's a paper that it's kind of a review paper, but it's not. Well, I guess it's not the review that we usually see in neuroscience. But it's so the topic is the representation of memory, how memory is encoded in the brain, and it comes from the computer science side. Um, so yeah, we can start with what they say is that memory might not be completely lost ever, but their hypothesis is that when we lose a memory, essentially we actually lose the address to the memory in the brain. It's um, simplified, but the idea is that the memory is still encoded in the brain, but we lost the way to access it. And they propose that it's because the memory in the brain is encoded in a key value fashion. So it's like so if you code in Python, that would be dictionaries, but also like basic dictionaries are working like that. You have a word, you have the um, if you have the index, you get to the page of the word, but the actual content is the definition of the word. And that would be the same for, in their hypothesis, that would be the same for the brain. We have a key that tells us where the memory content is, and then the memory content is what we are retrieving. Um, and for that, they are proposing, they start by explaining how we encode how we can implement these key value architectures. And when I read the abstracts, I didn't think it would be that hairy of a paper. So the beginning is all equations. So they are not like super complicated equations, but it's too complicated for me. Um, but yeah, so I'm gonna skip the equations, but basically they talk about different ways we can implement the key value um, mechanism, because in a dictionary you have a key, an exact key that gives you the definition, but in the brain and in our lives, we rarely have like we would not trigger the exact key. So it's more complicated than just having a list of keys, of exact keys, and then with the exact key you get the content. So there are some ways to encode similarity with the keys that then can trigger several memory contents. Um, and then you have to aggregate the memory content. And for example, one of these architectures is the transformers that we've heard about in recent years, because that's what has been used to improve, for example, large language models. But it also improved a lot of things in vision tasks like detection and segmentation and stuff. And basically, so I think it's one of the equations over here. Anyway, so basically a transformer can be seen as an approximate key. So it finds it associates similar keys together to find similar, then the contents that they are associated with, and then aggregates them, and you get an aggregate memory content in that case. And yeah, so their point is that the such structures don't really forget the content, but they might forget how to access it. So if we and they show it at the end, but if we train further on the same architecture but with a different task, it will learn the new task. But then they show that the memory of the first task is still in there, even though you can't access it easily. But of course, then they have to show that it would be working the same in the brain, because the first part of the paper is only about the computer science structures, architectures that we could use to emulate that mechanism. But then, is it actually working like that in the brain? Um, and I feel that that's the part of the paper that is a little bit too. I feel that they have a big confirmation bias. So they found a lot of evidence that go in their way, but they didn't do the usual job of a neuroscience review that would also document the evidence against their hypothesis of that it works like that in the brain. And for their example that it works like that in the brain, they hypothesized that the hippocampus would be storing the keys, and the neocortex would be storing the memory content. And one thing that they say that they highlighted is that they talk about backpropagation. They don't talk about another. So they also hypothesize that backpropagation would be used in the brain like we do in machine learning, and that's a big hypothesis. And also, we've actually saw a paper on that. I don't remember who presented it. I don't know if it was Lilith. A paper that was showing that backpropagation might not be what is used in the brain. So that's yeah. And they didn't mention that. I don't know if the paper is not that popular or something, but that made me think that they only took the evidence that helps them. So according to their model, oh yeah, there was something. I don't know if Marcella is here. There was maybe it's later, but I hope you're gonna have questions because it talks about some of the models that I think we discussed together. So what they are, according to their model, so the hippocampus would be encoding the keys, and then the cortex, the neocortex, would be recording the content. And their hypotheses are, memories are stored indelibly, but subject to retrieval interference. So that's one of the main points, is that we don't forget the memory content, we forget the memory keys. And then these keys are distinct, they have a different nature from the actual memories. And they also claim that these keys are not available to us, so we can't consciously recall keys, which to me is weird because you can. I mean, yeah, it seems like a very strong hypothesis because I feel that you can know what triggers a memory, like you can reflect on that. So and you can have some control on how you recall some memories. Sometimes you don't. I mean, we don't have full control of memories all the time, but we can control partially how we recall memories. So I feel it's a strong hypothesis. Um, Also, they talk about so their first argument for the brain is able to store memories forever is that the brain has a big capacity, a storage capacity, but they don't say, like, how much is that capacity, is that good, is that bad, because we are storing images, we are storing sounds, we are storing any kind of crazy complex data. um, I don't know what that means, so that paragraph, I don't feel that it's a good argument. Um, and also their other argument is that, oh, you can remember things from like super old memories, but you can't remember all of them. So that doesn't work as an argument for the permanent storage of memory. Um, so yeah, that's so they are listing all the points of the arguments for their model in working like that in the brain. Um, and yeah, one thing is that some of their arguments, they could be other solutions than the key value architecture to explain these things. So for example, the memory that's is stored forever, that could be another, there could be other explanations. um, um yeah, the memory, so they also say that the memory stored in the key value fashion is easier to optimize for accuracy of the content, um, which is also not really an argument for their model, because I think there are a lot of proofs that the accuracy of the content in the brain, of the memory that we retrieve, is not very good. I mean, there are a lot of examples of witnesses that are imagining things, and we all make up things all the time. Um, and yeah, most of the arguments is that sometimes we can, for example, sometimes we can recover the memories by stimulating the key retrieval. Um, but if it only works sometimes, that's not really an argument for your model. And yeah, that's the part for Marcella, the complementary learning systems. That's also one of their argument for the key value model, where they say that hippocampus is specialized in for episodic memory, and neocortical areas are specialized for semantic memory. um, and then they have their strong hypothesis, even like more specialized on the model of hippocampus and neocortex. But then, so they say that if you essentially what they say is that if the hippocampus is not working correctly, you don't have access to the keys to your memory, so you don't have the address to your memory, so you can't access them anymore. But HM had his hippocampus destroyed almost completely, I think. So, and yeah, he lost episodic memory, but he still had access to his old memories. So he still had the keys to his memory. I don't really understand how it's really an argument. I think they are going a little bit too deep in the match between computer science architecture and what we know of the brain, because we actually don't know that much details on how things are encoded in the brain. Yeah, they also say that the hippocampus needs to do some cleanup in order to retrieve the keys, which I don't really know what that means. Maybe I'm stupid. Maybe I didn't understand what they mean. But also, they use examples like the tip of the tongue experience to justify their model. Say, oh, because it's you feel like you know that you have the key. I don't understand how it would work, because you would need to know that you have that memory. So that means that your key mechanism is working, but not the retrieval. Um, I, it's I don't really get how it's an argument for um and also that means that you know about the key, so that's against their argument that keys are unretrievable. Yeah, I don't know about the arguments for how it works in the brain. And then they are doing some simulations. So they train machine learning models, simple models with the architecture that they mentioned at the beginning, the different mathematical computer science architectures. And they are training. So their first model, um, yeah, the first model is that they are seeing the representation of key values. And basically what they are saying is that key and values are even though you don't explicitly tell the model what is a key and what is a value, so what is a key to a memory content, the representation will be segregated pretty well in the network, if I understand correctly, um, which shows that they are encoded with a different nature, even though you give them as the same modality. You give two vectors, you give a vector of keys and a vector of memory, and in the end, in the network, they get completely separated because they have different roles. And the second simulation is that they train classic model to classify images. So they use the MNIST dataset, which is handwritten digits. And then, so once the model is reaching a decent performance, then they keep training it, but they change the output, the input, sorry. And they use the fashionist, which is, I think, a data set of pictures of clothing, pieces of clothing. And as they retrain the model, so it's the same model, and quickly the model reaches a pretty good performance in this task as well, recognizing pieces of clothing. So this is not surprising, but then the thing that they do is that they still have this key value implementation. So they give a key value inputs, and then if they increase the activation of the keys of the first task, apparently they can retrieve the performance that they had at the beginning. So even though we see that the performance in detecting, so the task one is the numbers, the digits, after they start training with the second data set, the performance in recognizing the first data set completely crashes. But if they increase the activation of the keys, they can, that's the second part of the plot, they can retrieve the same a good performance in the first task that was technically unlearned by the model, but they show that it was not actually unlearned. It was the access to the model was to the output was silenced. And of course, they say that that might be why in the brain we forget things. It's because the keys are not activated enough to trigger the memory content anymore. But if we reactivated them, we might access the content that is stored forever in their hypothesis. Yeah, and I highlighted that the connections between neuroscience and machine learning that they propose here is very speculative. At least they acknowledge that, so that's good. I think it is very speculative, and I think they got a little bit too deep in the match between the two. I'm not sure I actually agree with that. But their idea of key value might be interesting, in my opinion. There might be some mechanisms that are working like that in the brain. I think the example that they chose is too specific. So yeah, that would be all for this paper. I hope it was not too confusing. It was confusing for me to read it.
Thank you, Chris. The chat has been on fire while
I
you
saw that.
were presenting, and Eduardo already has his hand up, so I give the floor to Edo.
Thanks. Yeah. Thanks, Chris, for presenting. Interesting paper. I don't know what to think about the details, especially for figure 3, but let's keep it general. So if I got it right, what they say is like, oh, we trained this model on one data set and then we train it on another one, and yeah, guess what? The performance on the first one collapses, and then you can learn the second one. But if you twist these parameters, like somehow you can retrieve whatever information was there before. I'm a bit skeptical with the link to the actual neurobiology, but not even the neurobiology, the actual behavior of brains and then the way we store memories, because this would imply that if you learn new stuff, then the brain would forget it, which is it's not the way the brain works, right? If you overlay memories over memories, well, there could be interference, but memories could also reinforce each other. So it's
Yeah,
like if you assume this is yeah, you get my point?
That's true that the memory interference. So what they hypothesize is that when you learn things, well, that for them that could be a reason for their model, for their key value model, that you are not forgetting things because the only interference that you would have would be between the keys and not the memory content. So the memory content would still be encoded, but you could have interference between the keys. So how you retrieve the address to the memories, and that's why we could sometimes forget things. But at the same time, yes, we when we learn a new thing, it doesn't erase old things. But that could be justified with a key value because, well, especially because they are saying that you don't lose any memory. So that goes in their way that if we learn things, it's not erased.
Yeah, but you lose the key, so it's kind of also.
You
But
don't
also,
lose the key all the time. It's just that if the key is not, so what they say is that you would lose the address because it's not used essentially, which would which would be similar to what we know about like activations. Like the more you activate a memory or even any other function in the brain, it gets reinforced. So the key would be reinforced to stay in your dictionary. But if a memory is not used, the memory is not lost, but the key might fade unless it's reactivated somewhere, somewhat.
yeah, okay.
Yeah, I mean,
Yeah,
it's very hypothetical because, and especially because I don't think their examples are very compelling arguments.
mm,
So it I feel that it could be a good idea. It might even work like that in the brain, but not in the way that they describe it in the paper, I think.
yeah, because I mean, you have the case where you could just like lose keys by simply not using them, but yeah, so there's no need for overlaying more memories to lose memories. So yeah. Hmm.
Yeah,
Oh, we'll see.
their model could be interesting, but I don't know enough of neuropsychology and neurobiology to talk
Yeah,
too much about
yeah,
that.
interesting. Yeah, okay, thanks. Mish is bouncing.
He's just bouncing. I have to admit, I'm a bit lost with this paper.
I was a bit lost as well, to be
Yeah,
honest.
you made that point a couple of times, but also how it relates to like classical neuropsychological models of memory. And yeah, maybe it's too early on in Monday morning, but I'm struggling to connect the dots here. Marcella has a question for you.
So, thanks, Chris, for presenting this paper. Yeah, same as Steph. It was too much information for me. Like regarding the last weeks, I have been reading a lot about memory system, the theories. So it went to a totally different direction. So I was like impressed. But I'm wondering if like at some point they also, because I know they mentioned one framework that I guess is the most important or related to the
Yeah, the
more
complementary learning
computational,
systems.
yes, more computational
Did you
approaches
read
that.
that when you were reviewing the literature on memory?
No, no, not at all. But I think it's popular in more in the computational fields. But so I was wondering if they try to interpret the results in regard to the most classical theories of memory consolidation or the ones. So there is like two main ones. That one is uh, proposing that the hippocampus is always important for memory encoding and retrieval. But then there is another one that is the ones that have a lot of support, the two of them, um, saying that yes, hippocampus has a very important role at the beginning when the memories are recent, but then once they are consolidated and they become more remote, they are not like more important regions are at the neocortex. So it's maybe something as you mentioned, but I don't know if they try to relate the results in more classical theories. And also I was wondering if, well, so that's first. And then if they talk about a specific kind of memory, like episodic, and then how, I'm wondering how these kind of models can actually try to represent episodic memory, as episodics are in human brain, or yeah, these two questions I think are the ones
Yeah,
I have in.
well, first, that's surprising that they use a model, a brain model, the complementary learning systems, that doesn't seem to be that popular in the memory literature. That's a bit weird because they say it's influential, but it doesn't seem to be. So it seems to be a model that they chose that fits their hypothesis. But yeah, they do talk about hippocampus being specialized. So in their model, hippocampus would be specialized in episodic memory. So they define it as remembering events that occurred in a specific spatio-temporal context. And the neocortex would be specialized in semantic memory. So that's also pretty like generic. That's very broad, because then they also say that the hippocampus would have a role of noise filtering. So in the end, they are hyper specializing the hippocampus, but then they have to acknowledge that the hippocampus might be not that specialized. Um, yeah, I'm not sure. It feels like they are really trying to fit their a model, a neurobiological model that they found to their idea that memory would just be key and values. Um, I feel that they are simplifying way too much what memory could be, and yeah, they are not talking a lot. So they are very briefly mentioning episodic and semantic memory, and then it's pretty much gone. Um, Even though it seems to be a pretty important distinction in memory, and if they say that the hippocampus would be specialized in episodic memory, that would mean that episodic memory would be the keys to semantic memories. Does that make sense?
Mm.
So it's yeah.
Yeah, I don't know. I feel like yeah, it's very it's missing yeah, important how to say, ideas like connections also. Like it's not just hippocampus, it's not
Yeah.
just like so yeah.
Also, they're
Um
pretty vague on the inputs. They are completely, because also the toy examples, the simulations that they are doing, it's one modality, but the brain is never one modality. We always have auditory input, visual input, a bunch of different sensation inputs when a memory gets stored. And also like internal, just the internal inputs, um if two people were experiencing exactly the same thing, they wouldn't store it the same way because we have a totally different life. So um their model is so simplistic, I feel that their arguments for the neurobiology is too thin, in my opinion. But I think their model could be a track to find something.
And I have the last question. I don't know if Michelle wanted to do it, but to ask the questions. But he mentioned about the priming. I don't know if they mentioned something about
No.
how. No, okay.
I didn't read anything about priming, but yeah, actually there could be some interesting experiments that could go with their way or against. Maybe there would literally be a way to. So they talk about some experiments, but I don't think they mention priming. But yeah, it really feels like they only took the experiments that were working in their way, but not the experiments that would contradict their model. So that's the main reproach that I have with the paper, is that when they talk about neurobiology, they just selected the arguments that are working.
The general problem with those AI to brain papers, though, right? That even if you see the same outcome in the end, it doesn't mean you got there the same way. So the mechanism behind it.
Even though they mention it, the neurons have nothing to do with artificial neurons. They are completely different. They are regulated completely differently. Also, in computers, you don't have differences in timing. That's completely out of machine learning models. There is no problem with time.
But we have a problem with time.
Yeah, but
we're out of time.
I was thinking that. Perfect transition, isn't it?
Thank you. You served that on a platter. Thanks for presenting. I think we're all very confused at this point, but have an exciting week in science. And see you next week for the next Neuroccino, Monday morning, 9:30. Have a great week. Bye.
Bye.